All right, so last section we're going to take a look at is 3.2. Okay? And again, it has three different things in it: continuity, intermediate value, and end behavior. Okay, so we're going to start with continuity. All right. So when we draw something on the calculator, sometimes it draws it and it's connected the entire time. Sometimes when we draw something, it's in separate pieces and they're not connected. So let's just examine a couple graphs. Okay, let's start with that one. 1 divided by x minus 3. Okay, so let's just type it in. Whenever a numerator or denominator has more than one term, you always use parentheses. So you want to make sure you type it in just like that. Now, is there any number there that you're not allowed to fill in for x?
Yes.
Yeah?
Would it be 0?
0 is okay to fill in for x. That would give us negative 1/3 for y.
Okay.
So 0 is okay. Yep.
Is it 3?
3, right. We don't want to get a result of 0. And if you plug in 3, that'll cause a 0 in the bottom, and you can't divide by 0. All right, so let's look at the graph. So something weird is going to happen when we get to 3. That's what it does. So there's our first graph. Okay, let's look at another one. Let's look at what's called the integer function. So the integer function basically is a function that rounds the number off. And the way it rounds it doesn't round it properly. It always rounds down. So like if you plug in 4.9 into the integer function, it rounds it down to 4. If you plug in 2.3, it rounds it down to 2. So it rounds the number down to the next closest integer. Okay, that's how it works. So if we type that in, integer function, it looks like that. Because it's rounding, you never get an answer that's a decimal. That's why there's some gaps. If you plug in 4, it rounds down to 4. If you plug in 4.5, it rounds down to 4. 4.9 rounds down to 4. If you plug in 5, now it rounds to 5. So you never get an answer that rounds to a decimal because that's not what this does. It rounds to the nearest integer. Okay, so we have that one. And we got one more we're going to do. I'm going to type in x squared minus 2x plus 4. Okay, so let's clear that. X squared minus 2x plus 4. Okay, I'm using Zoom 6 for all of these. And we got that one. Okay. So we're going to look at each of these graphs in terms of what's called continuity. And we don't really know what that is yet. But out of the three, does anybody have a guess which graph would be considered continuous? Yeah?
The third one?
The third one, yeah. So the idea of continuity is, in kind of a simplified form, can you trace the graph without lifting your pencil? If you can, then you have a graph that is continuous. If you can't, then your graph is discontinuous. So let's write that down in a little bit different way. Let's say that I draw a function like this. There's my function. Okay, I'm going to mark some different points on it. Let's say over here is point A, B, C, D, E. Different points. So if a function is continuous over a certain interval, let's say we're looking at this interval right here, from A to B, that section I just traced. I'm going to name that interval or I'm going to name that section. I'm just going to call it section J. That's just the name I used. It's the name of the section from A to B. For that section to be continuous, it means that I can start at A, I can stop at B, and I never have to lift my pencil the entire time as I go from A to B. That's what it means to be continuous. So there's lots of sections there that are continuous. A to B, B to C, A to C, D to E. Those are all continuous. If you can't trace from a starting point to a stopping point without lifting your pencil, then you have a graph that is discontinuous. Can anybody name an interval on that graph in blue that is discontinuous? Yeah?
C to D.
C to D. You cannot trace from C to D without lifting your pencil. Yep. That's discontinuous. So with graphs, as you just saw in that last one, it is possible to find maybe some sections of the graph that are continuous and other sections are not. Right? I just asked for one that was not, and somebody said C to D. That's not. But I named some ones earlier that were. A to B, B to C, and a couple others. So let's look at a graph. And what I want to do is name two intervals. So in other words, you have to tell me a number to start at and a number to stop at that I can trace between without ever lifting my pencil. And then I want to know two intervals where I would have to lift my pencil, okay, because it would be discontinuous. Okay, and this is the graph we're going to look at. 1 over x. Okay, so let's put in 1 over x. Let's get the graph. Okay, calculator doesn't quite draw that completely accurately. It should continue up and down forever. What happens is because it's getting really steep and the calculator can't draw anything that's vertical, it just kind of gives up. And it's like, well, good enough. All right, it just doesn't do it. But if I fix it so it looks like what it really should look like, that keeps going down. That goes that way. And then it looks like that. It never touches any of the axes. It's probably easier to see that before I darkened it. But that's important. Never touches any of the axes. Okay, so let's name two intervals in that graph that are continuous. Can anybody give me an interval that is continuous? Yeah?
From negative infinity to 0.
Okay, so from, you said negative infinity up to what number?
0.
Including or not including?
Not including.
Not including. Yeah, that would be continuous. If you had enough time, you could trace from negative infinity to 0 without ever lifting your pencil. That's an infinitely long continuous interval. It's the entire bottom piece. Could somebody give me another continuous interval that is not infinitely long? Yep.
5 to 8.
Sure, just 5 to 8. Right? So 1, 2, 3, 4, 5 is right there. 6, 7, 8 is right there. There you go. 5 to 8 is a continuous interval. And you could include the 5 and the 8. You could not include the 5 and the 8. It doesn't really matter. You can trace between 5 and 8, and it will always be continuous. Yeah.
So with the square parentheses, does that mean it stops? It starts and stops?
The bracket means to include the number.
Okay.
It means it can equal the number. parenthesis means you cannot equal a number. So if River had said put a bracket on the 0, that would have been wrong, because you cannot include 0, because that would cause you to divide by 0. This graph doesn't exist at 0, so you can't trace to a number that doesn't exist. Right. How about discontinuous? Somebody give me an interval here that would be discontinuous. Yeah?
Negative 3 to 3.
-3 to 3, yeah. -3 is over here. +3 is right there. You can't trace from -3 to 3 without trying to jump across that gap. That's discontinuous. How about another interval that would be discontinuous? Yeah. -5 to what?
5.
Yeah, anything that goes through 0. So as long as your first number is a negative and your second number is a positive, in this particular graph, that will be discontinuous. I can't say that that's always the case, but in this one it is. Any questions on that? So there's different ways that a graph can be discontinuous. The reason why there's a discontinuity in this one is a different reason than why there are discontinuities in that one. First of all, this graph has one discontinuity. It's right when x is 3. This graph has infinite discontinuities, because it jumps. In this graph, the reason we have a discontinuity is because there's a number that could cause you to divide by 0. In the integer function, that's not the reason why there's a discontinuity. The domain here, well, what kind of numbers can you plug in and then round down? What kind of numbers are you allowed to round down? Yeah?
Any decimal that's like 5 or lower.
So remember, the integer function, it just takes anything and rounds down. It doesn't follow rounding rules like 5 or higher. So if you plug in 4.9 right here, you're going to get 4.
So is any number with a decimal?
Well, what if you plug in the number 3 and you round that down to the lowest integer you can? If you round 3 down, what's the lowest integer you can round it down to? 3, yeah, that's the next one. It's already added. So you can, if you plug in 3 there, you get 3. So you can plug in a number without a decimal as well. So what kind of numbers can you plug in? Yep. Well, we just said decimals too. Yep.
Is that only numbers?
All real numbers.
Oh,
You can plug in any number and round it down, right? Anything. Doesn't matter what the number is. You can always round a number down. Okay? And that's what this function does. It just takes any number and rounds it down. Doesn't matter what the decimal is, it gets rounded down. So the domain is all real numbers. You never have a case where you would divide by 0. But the reason you get gaps is because of rounding, right? Not because of dividing by 0. So there's different reasons why a graph might be disconnected. Okay. Dividing by 0 is an example of a graph having an undefined value. If you divide by 0, your graph is not defined at that number. You could also have breaks in the graph. Okay? A break is caused in this graph because of rounding. You're not allowed to give me an answer that's a decimal. So you could give me a 3, or you could give me a 4, but you can't give me anything in between the two as an answer because of what this function means to do. And because you can't give me decimals, you're going to have to jump from the number 3 to the number 4 without anything in between. Yeah?
So why when you put a regular number in place of x, it's just a straight line? Because like if I did like the integer function and you plug in like
Yeah.
it just goes straight, it's just a line. That's
Well, you don't always get the same answer. A straight line would mean no matter what you plug in, the answer never changes.
okay.
That's not true. If you plug in 7.4, it's going to give you 7.
Okay.
If you plug in 13.5, it's going to give you 13. So it's going to give you different answers depending on when you plug in, but it will never give you a decimal. Yeah.
Thank you.
Yeah. So we can have a value that's undefined. We can have breaks in the graph. Both of these are very easy to see. You look at the picture, there's no question those are discontinuous. The third type of discontinuity is impossible to see. It's called a hole. You have a hole in a graph. The only way that you can know your graph has a hole in it is if you have the original problem and you can look at that. Let's type in that and graph it and see what it looks like. So in parentheses, let's type in x squared plus 3x plus 2. We're going to divide by x plus 2. I'm going to do zoom 6. And if you look at that graph, before I let it finish, what number are you not allowed to plug in for x there? What is it? Why not?
So you'd be divided by 0.
Right, if you plug in -2, you'd be dividing by 0. And I want you to look at what happens on the graph when x is -2. What does it look like happens on the graph when x is -2?
Nothing.
Nothing. -2 is right here. So if you were to look at that graph, and that's all that I showed you, would you say that that's continuous or discontinuous? Looking at the graph, it looks continuous. But if you go to your table and you try to plug in -2, it says there's an error. Okay, because you are dividing by 0. You can't use -2. So what happens in this graph is there's a hole, and that's how you draw it. I wouldn't even draw the line going through the hole. I would just do it like this. That's the symbol for a hole in the graph. It's basically an infinitely small break. That's what it is. It's so small you can't see it looking at the graph. You only know that you have it if you can look at the original problem. How could I rewrite the top if I factor it? How does x squared plus 3x plus 2 factor? Yeah?
X plus 2, x plus 1.
X plus 2, x plus 1. This is the reason why there was a hole. Because we had a common factor in the top and in the bottom. That's when you get a hole in the graph. If you have a common factor in the top and the bottom. So it's basically like the x plus 2 cancels out, and all you're left with is x plus 1. Well, if you graph x plus 1, it pretty much looks identical to what I had. The difference is graphing x plus 1 is continuous. There is no hole. Graphing what I have here is discontinuous. Okay, the blue one had a hole in it. Now, how could I mess up the problem, let's say the numerator, so there isn't a common factor anymore? What could I do? Yep.
I don't know.
So how could I make it so the top doesn't factor like that anymore? Yep.
Flip them
Yeah, we can flip one of the signs or just change one of the numbers, right? You still can't plug in -2, because that would cause you to divide by 0. But look at the graph now. Right? It looks completely different. Okay, completely different. Because the top doesn't factor into something that's in the bottom now. Okay, we messed up factoring. Okay. So the hole is the trickiest one to look for. You can't, no matter how much you zoom in, you'll never see the hole in the graph. You gotta look at it, factor it, and then see if there's anything in common in the top and the bottom. So, any questions on those 3 types of discontinuities? The first one and the third one are really the same. They're both dividing by 0. The difference is the first one you can see very easily on a graph. The second one, you can't. It's impossible to see. All right, so that's the main idea of continuity. The nice thing about polynomials, okay, when we sketch polynomials, like linear, quadratic, cubic, things we talked about yesterday, they are always continuous the entire time. Okay, if you want to draw a parabola, do you ever have to lift your pencil from beginning to end? Nope, you never do, the whole time. Same thing with a cubic. Okay. Start somewhere, draw, and then end. You never lift your pencil when you draw a polynomial. So if you have a function that is continuous everywhere, no matter where you start and where you stop, that is called a continuous function. So in other words, in a polynomial, if I said to you, find an interval that is discontinuous in a polynomial, that's impossible. There is no section in a polynomial that you ever have to lift your pencil for. The entire function is continuous forever. From -infinity to infinity. Any question on that idea? Okay. So the next topic we're going to look at connects in with this one, and it's called intermediate value. When you think of the word intermediate, what does that mean? Intermediate. Yeah?
Does it mean like sometimes? Or no, that's it.
What does that mean? Intermediate. Yeah?
Medium?
Medium?
Yeah.
Like in the middle, right?
Yeah.
Like if you were an intermediate golfer, right? You're not a beginner, but you're not a pro. You're in the middle somewhere. So we're going to look at intermediate in terms of numbers. Right? If I had say a pot of water and it was at 70 degrees, it was like room temperature, right? And I start to boil, and it gets all the way up to 212 degrees. It started at 70, and when it gets to boiling, it's at 212. How many temperatures does it go through in between? How many? How many is a lot? Yeah?
As much as the time between when you first put it in the pot and when it starts to boil it to 12.
So how many temperatures is that?
What did you say when it
142? More than that.
Oh, would it be infinite temperature?
Infinite temperatures. Because if you boil something from 70 to 212, there's a time when the water was exactly 84 degrees. There's also a time when it was 85.7. There was a time when it was 93.624. Right? It goes through every single possible number between 70 and 212, and it can't skip any. That's not possible. It's a continuous process. Right? Just like, same idea if you were to stretch a rubber band. If it started at 3 inches and you start to stretch it to 5 inches, how many different lengths does it go through in between? Infinite. There was a time when it was 3.4, 3.91 inches. Right? It's continuous. It doesn't just skip. Now, if you compare that to me counting like people in the room, 1, 2, 3, 4, 5, 6. Did I count every number between 1 and 6? No, I skipped 1.7, 1.84, 2.416. So I skipped a lot of numbers. Bless you. Same thing on like if you use like a radio in your car. If you've got buttons to press, right? You might go directly from one station, like 96.1, directly to 104.5. You didn't go through every one in between, unless you have an old radio where you turn the knob. Then you go through every single possible frequency in between. But with newer ones, you just press the button and it just jumps. It skips everything in the middle. All right? So we're going to focus on ones that don't jump, okay? Things that are continuous. And the idea is that if you have something that is continuous from, let's say, A to B, okay, let's draw something. So that's going to start at A, and it's going to end over here at B. Okay, what's the y value? Like, how high am I, up and down? I don't know. I would have a formula that I could plug A into and find the y value. And then I'd have a formula I could plug B into and find that y value. So I have 2 points that are on a continuous section from A to B. What that means is as I travel from here over to here, I will hit every possible y value between this one and that one. So if, let's say this y value was at 5, I'm just making up a number, and this y value is higher. It's at 15. I'm going to go through every possible y value between 5 and 15 at some point. Okay, am I going to hit 6 at some point? Yep, maybe right about there. 7, 8, 9, 10, 11. I'm going to hit every single y value between 5 and 15. That's the intermediate value property. Okay. Any question on that? Yep.
Like, if we had a problem with that, would you ever ask what the domain and range of that is, or no? Because I mean, it's like infinite between what you said and
No, we wouldn't really talk about domain and range with this.
Okay.
No. Okay, we're just talking about the y values that we would hit. And the y values you would hit is anything that's basically in that purple section. Guaranteed. You're going to hit everything between 5 and 15 at some point, because you're traveling between the two purple lines and you're never lifting your pencil as you do it. Now, could you hit values that are more than 15? Sure. You could. Maybe you're going to travel there like this. I can't guarantee that you're going to go higher than 15. I don't know that. But I do know that you are going to hit everything in this range, because you're traveling from a value that started here and ended here. So you're going to go through everything in the middle. Any question on that? All right, so let's look at an example. So in the example, they give us this function. F of x equals 3x minus 4. What would that be if you draw it? F of x equals 3x minus 4. Yeah?
Linear.
Linear. And linear is a type of what?
Degree.
Well, yeah, it's a degree 1. And all those things that we gave degree 2's fall under a big category. They're all
Polynomials.
They're all polynomials. And what did we say about polynomials? Yep.
They're continuous.
They are continuous. Okay. Okay, so this is a continuous function. That's the first thing to recognize. We're about to apply this theorem, but if you're not working with something that's continuous, then you can stop right now. Okay, this isn't going to work at all. So I've got a continuous function, and they want me to prove that I'm going to pass through the value 15 at some point, the y value of 15, between this x value and that x value. Yep.
How would you know that the 3x minus 4 is a polynomial?
Because it fits the pattern of something that's like y equals mx plus b. And we know that y equals mx plus b is the slope-intercept form for a line, and lines are polynomials.
Okay, thank you.
Yep. Okay, so they want us to prove that we are going to pass through the number 15 at some point. This is a y value. These are x values. What do you think I have to do with my x values to prove that I pass through 15 at some point? Yes? Yeah.
Do you gotta put them into the equation?
Yeah, let's plug them in to the equation. Okay, they've given me this right here. They gave me an A, and they gave me a B. Well, what are the actual y values for those points? That's what's important. I have x values, I need y values. And then once I know my y values, I can tell you what numbers I'm going to pass through. And then I can answer if 15 is one of them. Okay. So let's plug in -10 first. What do you get if you plug -10 in for x? Yeah, you get -34. And what do you get if you plug in +10?
26.
26. So as I travel on this graph from -10 to +10 on the x-axis, what are the y values I'm going to travel through? Yep.
-34 and 26.
Right. I'm starting at -34 on the y-axis, and I'm traveling up to 26. So, and it's connected. The entire time the graph is connected. So am I going to pass through 15 at some point? No, why not?
Never mind, yes.
How come?
Because I didn't see it was -34.
So why am I going to go through 15?
Because if it's a continuous thing from -34 to 26, 15 is between
Right.
-34 and 26.
15 is an intermediate value between two numbers that we're traveling between continuously. That's the important thing to understand. Right. Now, the easy part, they want to know where do you hit 15? Right? It's somewhere between -10 and 10. Okay, we don't know where, but you are going to hit it. So to find out where you're going to hit it, plug 15 in on the left-hand side and solve. Right? And this needs to come out between -10 and 10, but we already know it will. So what was it? 3x minus 4. So add 4. And my last step would be divide by 3. And I get x equals 19 thirds. Is 19 thirds between -10 and 10? Yeah, it's like 6 and a third. So yes, it's between negative 10 and 10. Okay? But figuring out this number wasn't really that important. This was the important part. Understanding why you have to go through the number 15 between negative 10 and 10. Now, will I go through the number 30 at some point? No, not on a line, okay? Because a line is going from here to here in a direct path. The highest you ever go is 26. Now, what if it wasn't a line and it was a curve? Is it possible I could hit 30? Yeah?
I actually have a question.
Yeah.
Why did we have to plug in the negative 10 and 10? That wasn't even part of figuring out the final answer.
So that was to prove why you were passing through the number 15. That's what I wanted to prove. I wanted
Oh, I see.
to prove that 15 was an intermediate value as you travel continuously between that number and that number. This last part, I don't even really care about that much, but they had us actually figure it out, so I did what the book did on that. So back to my other question. If I travel from here to here, this is at negative 34, this is at 26. Could I pass through 30 if it wasn't a straight line? No?
It ends at 26.
No.
Still.
Did I pass through 30 now?
No.
Oh.
Remember, these are y values.
Oh, yes.
Yeah.
Right, this is like negative 10, or what is it? Negative 10, comma, negative 34. This is positive 10, comma, 26.
Okay,
So
well,
yes.
yeah.
I thought
So-
you were talking about next.
Yeah, I could pass through 30 if it's a curve, but I can't guarantee I'm going to pass through 30. I don't know if the curve is going to go that high. The only thing this theorem guarantees is you will pass through every number between negative 34 and 26. Maybe more, but definitely all of those. Okay. That's the important thing to understand. All right, so the last thing we're going to look at is what's called the end behavior. So when we draw a polynomial, the ends of it are always going to look a certain way. Sometimes they go up on the right, up on the left. Sometimes it looks like that. Down on the left, up on the right. Well, there's a way to tell what it's going to look like without having to graph it. And that's what we're going to look at. So we don't care what's happening in the middle. Who knows what the graph is doing in there? What we care about is what's it doing on the ends of the function. Like, is the right side heading up forever and the left side heading down? Okay. What's happening way over here and way over here? That's what end behavior is. Okay. So one way that we can describe end behavior is with arrows. This arrow describes what is happening on the left side of the function. This arrow describes what's happening to the y value on the right side of the function. So let me draw a picture that would go with those arrows. It would look like this. Okay, that graph matches those arrows. On the left side of the function, look at what's happening to the y value. It goes down. On the right side of the function, look what happens to the y value. It's going up. So that is how you would describe that picture right there. Now, if I had one like this, let's put a little different graph. Let's do x squared. These arrows are not going to describe the graph I have there. On this one, as you head to the left, y value goes up. As you head to the right, y value goes up. In that case, the arrows are both up. Okay, so there are 4 different types of end behavior. Both up, both down, down up, up down. Those are the 4 types. And I want to show you a way you might see in the book the way that they describe these. Okay, I use the arrows a lot, but there is another way you can do it. And let me start by just describing this arrow in this one. So I'm just focusing on the lower right one. The way you can describe this in words is to write this. So I'll write it first, and then I'll explain what it means. Okay, the way you pronounce that is the limit of f of x as x approaches negative infinity is infinity. And this one, I could describe almost pretty similar, but I have to change one thing. The limit of f of x as x approaches infinity is negative infinity. That's how you would describe this arrow on the right. So what does that mean? F of x is another name for what letter? Y. So this, and the word limit basically means what happens to. What happens to y as x heads, which way is infinity on the x-axis? To the right. What happens to y as x heads to the right?
Goes back.
It goes down. Where is down? Negative infinity. The blue one says, what happens to y as x approaches negative infinity, whereas x heads to negative infinity? Which way is negative infinity on the x-axis? To the left. So what happens to y as x goes to the left? As x goes to the left, look at your arrow. It's pointing up. That means the graph would look something like this. As you head to the left, you're heading up. Infinity means up. Negative infinity over here means down. So it's exactly the same thing. This is called limit notation. This is just arrows. There's no name for the arrows. Yes.
So for the other one, that looks just like it, but it's the opposite. It
This
would be
one?
the same, yeah. Wouldn't it just be the same thing, but
So if I was going to describe this one,
that one would be purple.
you always say limit of f of x as x approaches. That part never changes.
Okay.
Now, this is the left side.
Yeah.
The left side means I'm heading to negative infinity.
Okay.
This is how you always write what's happening to the left arrow. The purple is how you always write what's happening to the right arrow. Now, what you put in that box, you have to look at the actual arrow. This arrow is pointing down, so it would be negative infinity. This means as you head to the left, your graph heads down.
And then so for the right air, for the air going up, it would be f of x up to whatever, and it'd be positive infinity is equal to positive infinity.
Yes, it would be this.
Okay.
So this means as you head to the right for the x, the y heads up. So this is describing whether you're heading left or right. This is describing whether you're going up or down.
Gotcha.
This arrow is describing what's happening on the left. This arrow describes what happens on the right. And then the direction the arrow points tells you. On the right, you head up. On the left, you head down. Yep.
Would this be a question on the quiz? And if so, how would it be worded?
You'll see. So example 5, identify the end behavior. Okay, let's look at x to the 4th. So we can graph it. We get a picture of it. There's our picture. I'm not going to do it with limit. I just want to do the arrows because of time right now. What's happening as you head to the left? Yeah?
It goes up.
It goes up. What happens as you head to the right? It goes up. This is for f of x equals x to the 4th. This negative, without resketching the whole thing, the negative would cause the graph to flip. So what do you think the end behavior here is?
Both arrows are going down.
Both arrows are going down. So what we want is a way that we can just look at the problem and tell, without graphing it, are the arrows up, down, or one of each. And there's an easy way we can tell. All we have to do is look at, let's say we had something like this. There's several terms in that problem. There's only one term you need to look at that's going to describe the direction of the arrows. This one. That's called the leading term. The leading term is the term with the biggest exponent. That term alone controls what the arrows are going to do. Do these other ones matter? No, not for the arrows. They matter for the little details of the graph, but as far as are they up or down, all you have to do is look at the leading term. That controls the whole thing. And when you look at the leading term, there's two things to look at. This exponent, that's the end, and then the number that's in front. I call that a sub n. If this exponent is an even number, then you're always going to think of like a parabola. Parabola is an even number, x squared. The arrows are going to always go the same way. Even number goes the same way. Both up, both down. Odd numbers, like x cubed, you get one of each. Up, down, or down, up. To figure out that part, look at the number in front. If it's positive, you're going to be one of these top rows. If it's negative, you're going to be one of these bottom rows. So 3x to the second. Which end behavior would that be? Yep. Let's see. Even exponent. Yep. Positive number. Yep. That fits that one. Even, positive. If it was even and negative, then that one. So this leading term has a name. It's called the EBM. End Behavior Model. So EBM. So when we're looking at, yeah.
I forgot to give this to you this morning.
Thank you. I'm going to abbreviate this EBM from now on. So in this particular problem, if I asked you for the end behavior, that's where you tell me the two arrows. up, up. If I ask you for the end behavior model, you would say 3x squared.
Can you
That's
repeat
the, so the end behavior model is the leading term. The end behavior is up, up. So the difference between what's the behavior and what's the model. The model is the actual term. The leading term is called the end behavior model. So let's just, I'm not going to graph that one, but let's just look at example 7. What's the EBM and what's the behavior? So let's start with the EBM. What's the term there that tells you what the arrows are going to do? Don't care about the arrows yet. Yeah? So what goes in that box? Yep. So negative 0.5 x to the 4th. That is the end behavior model. Now, what's the end behavior? The end behavior is the look. What does it look like? Yeah?
Both arrows are pointing down.
Both arrows are down. Even, negative. Down, down. So that's the model. That's the behavior. And that's 3.2. Okay, so homework is up on the board. That's 161. What I'll do is while you're at lunch, I will list the topics that are going to be on the test. And that'll be in the video on YouTube shortly. Just a reminder, I will be after school today. And make sure you have your Chromebook for the test tomorrow.